let's start with the lectures today. Okay, so I have attached the video about the introduction of partial differential equation. Okay, so what we have done previously from chapter 1, chapter 2, and chapter 3, we have solved the ordinary differential equation, where chapter 1 discussed about first order. Okay, and then chapter 2 we discuss about second order, and chapter 3 we discuss about using the Laplace to solve the first order or second order of ordinary differential equation. And then we proceed with Fourier series, where we are going to use some sort of Fourier series knowledge in our chapter 5, which is solving partial differential equation. Okay, so what is partial differential equation? All right, so let's go briefly about this. I'm not going to go details, but I'm going to explain another example instead of one example that I have showed in the video. Okay, so what is partial differential equation? Okay, the partial differential equation, the PDE, okay, is when the equation contains at least one partial derivative of u. So if you have a function of u, where that function of u is in terms of x and y, then if at least one partial derivative of u exists, then we call it as a PDE. So you know that u is a function of x and y, and then if there is at least ux or u double x or uy or u double xy, where this is a derivative of u with respect to x, derivative of u with respect to x about twice, derivative of u with respect to y, derivative of u with respect to x and y or y to x, or derivative of u with respect to y about twice. Okay, if at least one of these partial derivative exists, then we call it as a PDE. Okay, so for this chapter, we are going to focus on how can we solve the PDE. Okay, so there are examples of PDE that we're going to use. Okay, so here we have a wave equation, heat equation, Laplace equation, all right, and then the difference is about their dimension. One dimension is only involve u, x, and t here. Okay, here u, x, and t. Two dimension u, x, and y. Okay, this one, two dimension u, x, and y, and t. And then three dimensional, we have u, x, y, and z, right? So for this, these are the examples of PDE that is used in our real life application. So how can we find the solution of this? By understanding what is the PDE itself, right? So now we have MSV. Okay, so in order to use this MSV, you have to know what is the expected solution. Okay, what is the expected solution that you want to seek? Okay, so now let's say we have here what? We have here a heat equation. Okay, this is discussed already, right? In our video. Okay. Can you see the screen? Okay, so now here for this PDE, we are going to use two methods. Okay, MSV and also D'Alembert. So I have showed to you in the video one of the methods, which is MSV. Okay, D'Alembert is quite easy, so don't worry. So method of separation of variables. Okay, how can we use this method? So first, let's consider one example where this is heat equation. Okay, now you can see here this heat equation involves U, X, and T. So you expect that the solution should involve X and T. Okay, so the expected solution is in terms of X and T. Okay, where X is some function of X and T is some function of T. And you have to differentiate. Okay, you have to differentiate according to the problem, where in this problem we have del u del t. Okay, we have del u del t. So we have also del squared u del x squared. And the expected solution should consist of x and t. Okay, how can we use MSV? All right, so first you expect the solution should be uxt. All right, then you differentiate according to the differential, according to the partial derivative involved in the problem. So here we have del u del t, which means ut, del squared u del x squared, which means u double x. So that's why you differentiate. Differentiate what? Differentiate the expected solution, our assumption. Okay, once you differentiate, you substitute to the heat equation. This is the heat equation. So del u del t now is ut x t prime, x t prime. K squared is k squared. Del squared u del x squared is x double prime t. So once you substitute, you rearrange so that we have x with x and t with t. Okay, and those equations are equal where when there exists any constant such as lambda. So you can separate these two equations to one equation and second equation. Okay, so by separating these two equations, we can have x double prime minus lambda x equals to 0, t prime minus k squared lambda t equals to 0. So starting with this problem, so here is your problem, and you expect that these are the solution, and you differentiate according to the problem, and then substitute and rearrange so that you have these two equations. Why we should have these two equations? Because we want to solve this PDE, and in order to solve this PDE, it is easy for you to reduce this PDE to ODE. As you can see, this is ODE, right? Previously, what we have done, we solved ODE. So it is quite easy for us to solve ODE, but instead of PDE directly. So this is how we reduce, right? And then we consider the cases. Okay, understand or not? The idea behind the solution of PDE. Anyone has question? I have repeatedly explained the same thing according to the video here. Understand or not? Okay, right. So now, once you reduce, of course, we want to find the solution, right? Okay, how can we find the solution? So what I have discussed here is how, right, is the steps in the method of MSV once the variables are separated. So this is the separated version. Then the solution process will be proceeded by applying the conditions. Okay, so this is how you separate. Okay, I think this is quite easy. Okay, so there are three types of PDE, all right, that we're going to use. Okay, so here we have 0 endpoints. Okay, both use U and has 0 and 0 endpoints. Insulated, where it use UX. Okay, when you want to apply the condition, you have to find UX first, where UX is derivative of U with respect to X. And the mixed endpoint mix u and also ux. So it uses the solution of uxt and also the derivative of u with respect to x. So the example that I have shown earlier is 0 endpoints. All right, even though there are three types of endpoints here, three types of boundary conditions here, the steps of finding the solution are all same. Okay, so now we have discussed 0 endpoints in the example 1 here. So as for today, let's discuss the second example. All examples here use the same process. Okay, but sometimes for this example, okay, as you can see, first you reduce to ODE, right? And then you change the condition and you need to consider all cases. Okay, for this example, as you can see, case 1, we put no interest in case 1, we put no interest in case 2 because the solution is 0. Then you just focus on case 3. Okay, but there are cases where all cases has the solution. And sometimes 2 of them has the solution. So we need to consider all of the cases, the value of lambda there. Okay, now let's try another example. Insulated endpoint. Okay, as you can see, this is a PDE where the condition use the insulated endpoints where it involves ux in the condition, where you have to know that you need to differentiate the u function with respect to x once you want to apply the condition. Okay, so what is our first step from here? Okay, first you need to understand what is the problem. So the problem here involves heat equation. Okay, heat equation where it involves del u del t, del squared u del x squared. So you have to know what is the expected solution of this problem. Okay, it involves u, t, and x. So what is the expected solution for this problem? Anyone? Ut, uxx. The expected solution means the solution of this problem. So we expect that this del u del t, del squared u del x squared should have the solution of u in terms of x and t, okay, where it should consist x and t. So this is our expected solution. Just like the previous example, we have also heat equation, but for this, this is 0 endpoints. So our expected solution must has u, x, and t. Okay, then when you know your expected solution, then you can find the derivative according to the problem. So here we have del u del t. So you should have ut. Okay, and here we have del squared u del x squared. So you should have u double x. Where ut, you just differentiate x once. Okay, and then u double x, sorry, ut is t. Okay, and u double x here, you differentiate x about twice. Okay, understand or not? So this is your expected solution. And then you differentiate the solution according to the problem. According to the problem, you should have del u del t. Okay, you should have del u del t where it is ut. And you should have del squared u del x squared where you should have u double x here. Where this one, you just differentiate t about once. And this one, you just differentiate x about twice. Clear or not? So this is your first step. Okay. Then what? Then you should reduce the PDE to ODE. How? By substitute to the PDE. So now this one, substitute to the PDE. Where the PDE involve del u del t. Del u del t here is ut. So xt prime equals to, okay, the PDE should have del u del t del squared u del x squared. So del u del t is ut. Alpha squared del squared u del x squared is u double x. So ut is what? Ut is xt prime. Alpha squared u double x is x double prime t. Okay, so from here, you should rearrange according to the variable. So you have x double prime over x equals to t prime over t alpha squared. Okay, and these two equations are equal where when there exists a constant of lambda, so we can just separate the equation according to the variable to 2 ODE. So now from this PDE, this is your PDE. Now it is reduced to this ODE. We have two ODEs equation where we can separate this, rearrange, where we can have x double prime minus lambda x equals to 0, t prime minus alpha squared lambda t equals to 0. So we have first equation, we have second equation. So we have two ODEs now. Okay, clear now? Any question? So far so good? Same process with the previous example. Okay. So now what we are doing just now is we reduce the PDE to ODE by expecting the solution and then differentiate according to the problem. Okay, so according to the problem, this is heat equation. So you should have del u del t, del squared u del x squared. So you differentiate according to the problem and you substitute to the PDE, rearrange to have these two ODE. So our solution now is focusing on these two ODEs equation. Okay, so how can we solve it? Before you can solve, you need to proceed to second step where you have to form the boundary condition because this condition is given to this PDE. But now we have ODE. So we need to have the condition for this ODE. Okay? So for this case, the boundary condition given is, the given condition is ux 0t equals to 0, right? And ux lt equals to 0. And the expected solution is in terms of uxt. Okay, previously, right, as you can see, previously, in order to form the condition, we just can use this u. This u, because this is 0 endpoint, it only involves u. But now, this insulated endpoint involve UX. Okay, so what should you do? You have to differentiate. Differentiate what? Differentiate the expected solution. This one. Okay, differentiate so that we can have UX xt equals to x prime x. Okay, so now for this ux 0t, so ux 0t equals to x prime 0 tt equals to 0. Just substitute x here with 0 and then equals to 0. So from here, you can have x prime 0 equals to 0. Is that clear? Another one, we have uxlt equals to x prime x tt, right? So this one is L, this one is 0. Then we have when x equals to L, it equals to 0. So we can have x prime L equals to 0. So we have two conditions of ODE here. Is that clear now? Any question? Okay, if you have question, you can ask. We are having a long time, a long road here, a long steps here until we reach the solution. If you have problem, directly ask. No need to wait. Okay, so now we have done with forming the ODE and also forming the boundary condition for ODE. Okay, we have the ODE and we have the boundary condition for ODE. So we can proceed with finding the solution of this ODE. How can we find the solution? Because we need to find, okay, solving the ODE by considering all cases of lambda because we have lambda value there. Okay, so we need to solve this ODE, this function, by considering all cases of lambda. Okay, so let's proceed. Case 1, where lambda equals to 0. Alright, so we know that we have two ODE here, x double prime minus lambda x equals to 0, t prime minus alpha squared lambda t equals to 0. So these are the ODE that you want to find the solution. Okay, and in order to find this solution, we need to consider all cases of lambda there by starting with case number 1, where lambda equals to 0. So when lambda equals to 0, okay, when lambda equals to 0, what we have, x double prime equals to 0. Okay, focus on first equation first. We have first equation, we have second equation. Start with the first equation and proceed one by one. Right, so when lambda equals to 0 here, from the first equation, we know that x double prime equals to 0. Okay, when x double prime equals to 0, you know that this is homogeneous, and by characteristic equation, you know that m squared equals to 0, where we should have two roots of m1, m2 equals to 0. And you know that your x solution should have what? Exponent to the power of 0 times a plus bx. So x equals to a plus bx. So this is how you solve the second order of differential equation in chapter 2. You change to the characteristic equation, okay, understand the types of roots and identify the solution. So now you have x equals to a plus bx. And remember, we have condition of the ODE. So we have these two conditions. Okay. But here we only have x. So in order to match with the condition, you should have your x prime. So x prime here equals to what? X prime here equals to b. Okay. X prime 0 equals to 0. So x prime 0 equals to 0 and here equals to b, then b equals to 0. Right. Okay, so when b equals to 0, then x equals to a. Is that clear? Then second condition, x prime l equals to 0. X prime equals to 0. X prime l equals to 0. Is a affected by this condition or not? Not affecting a because a here is alone, is constant alone. So the solution is, then the solution for this case, lambda equals to 0 is x equals to a. So this is one solution that you obtain from the first case here. Is that clear or not? Anyone has question? Okay. So for this case, we have find the solution of x. Then we can proceed with find the solution of t. Okay. Still in case 1. So now proceed with second equation. So now from 2, when lambda equals to 0, t prime equals to 0. Right? Characteristic equation will give you m equals to 0. Okay. When m equals to 0, we have here only one root. Then we can have the t solution equals to a, this is ab, c, e, m, x, where m here is 0, then t equals to c. Okay, so we have the solution of t. And remember, our expected solution is uxt equals to xx dt. So from the first case, u1 xt equals to x is a, okay, t is c, this one. Then both are constant, then we can have the first solution is given by t, let's say, another constant. Okay, clear not for the first case? Any question? Yes? How we find t prime? Okay, change to the characteristic equation. Remember, double prime will give you m squared. So, t prime will give you m. And directly m equals to 0. And you know that this is only involve only one root. Okay, so if it involve only one root, automatically you go for distinct. And for distinct, we have what? The solution for distinct, usually we have y equals to AE M1x plus BE M2x. But now we only have one root. So just focus on one part. So T equals to CE MX. And M here is 0. Then T equals to C. Okay, clear? Okay. Why we proceed with equation of T, but in example 1, we don't do this? Okay, why? In example 1, as you can see, in example 1, the previous example, case 1, lambda 0, give you x 0, right? X is 0. Sorry. X is 0. You obtain x is 0. So remember, once you obtain the solution, you must always go for the expected solution. When x is 0, then no point to find t because it will give you 0. So that's why we don't proceed. That's why we always start with finding x first, okay? And then we proceed with t. If you have your x equals to 0, then we just put no interest with that case. No need to find t. But for this example, our current example here, give the solution for x, where x equals to a, okay? And remember, our solution should always stick to our expected solution, where when you have x, you should have t. Now you have x equals to a. Of course, you need to find t. If your t equals to 0, only then we put no interest for this case. But now we have t equals to c. So we have the solution for this case. Is that clear? Okay, good. So remember, this is the first solution. Right, so that one is for case 1. Okay, now let's proceed with case 2. What is case 2? What we need to consider in case 2? Lambda should be greater than 0, right? So let's say lambda equals to p squared. Okay. Of course, we have to always consider these two ODE. Okay, so from the first equation, you know that x double prime minus lambda x equals to 0. Now, your lambda is p squared equals to 0. Okay, so we have m squared minus p squared equals to 0. So for this case, m equals to plus minus p. Okay, and as you can see, we have two distinct roots of plus minus p. Then you should know that the solution of x should have AE m1x plus BE m2x. Then we have x equals to AE px plus BE minus px. Okay. Then what? Then apply the condition. And the condition involved with x prime 0, x prime L. So we have to find x prime first. So for this case, our x prime equals to what? PA EPX minus PBE minus PX. So we can just factorize P outside here, AE PX minus BE minus PX. Okay, the first condition is x prime 0 equals to 0, right? So now x prime 0 equals to 0. Substitute x 0. So P A minus B equals equals to 0. Okay. Then for this A minus B equals to 0. Eliminating P here. A equals to B. Right? So now when A equals to B, then just substitute here. Now your XX equals to A EPX plus E minus PX. Right? Just substitute A here equals to B. Alright? B equals to A and then substitute and then factorize. So we have X equals to A EPX plus E minus PX. So this is once we apply the first condition. Okay, now the second condition, X prime L equals to 0. Okay, X prime L equals to 0. So just substitute X with L, right? Just substitute X with L. Okay, so we have X prime here, this one. Okay, P A, because now we have A, so just put A outside. EPL minus E minus PL equals to 0. Okay. Then we have EPL minus E minus PL equals to 0. Okay. P here cannot be 0 because P greater, because lambda is P squared here and lambda greater than 0. So you know that this P cannot be 0. Then just put P to the right and then we have A. Then from here we can have A equals to 0. Okay. And then once you know that A equals to 0, then the solution of X from here is 0. So once you know that X is 0 and you know that the expected solution of UXT is always equals to XXTT, and since X is 0, no need to find T. So U2, the solution of second case, then we just put no interest. When you got 0, then we put no interest. Is that clear for the second case? Any question? Then for this case, no need to proceed with finding T because we get X equals to 0. No need to follow the sequence. Because at the end, we are going to sum up all 3 cases. Okay, understand? For the second case here. Anyone has question? Yes, indeed. The solution is quite long, but once you understand, you can get it. So the key point here is understand or not? Because the steps are similar. Once you can try to do the next example, as you can see, it follow the same pattern. Okay, just the solution is quite long. Okay, all clear for the second case? So this is your first solution. This is your second solution. All right, are we good, guys? Can you proceed? Okay, thank you. So now, done with case 1, case 2, and then case 3. So case 3, we consider lambda less than 0. So be lambda negative p squared. Okay, where we know that from the first equation x double prime minus lambda x equals to 0. Okay, then just substitute x double prime minus plus p squared x equals to 0. By characteristic equation, we have m squared plus p squared equals to 0, and this is a complex root, will give you m equals to plus minus pi. So since this is a complex root, then you know that your x solution should be a cos px plus b sine px, right? And remember, our condition is x prime 0 equals to 0, x prime L equals to 0. Okay, so from this, you should have your x prime x. What is your x prime x here? Should be negative PA sine PX plus B PB cos px. Just differentiate x here with respect to x once to get x prime. Okay, and then apply the condition. So for this case, x prime 0 equals to 0 will give you what? So this is 0, negative PA sine 0 is 0, plus PB cos 0 is 1. So 0 plus PB. Okay, and then PB equals to 0. So for this case, B equals to 0. Okay, now when B equals to 0, then what's left? X prime x equals to negative PA sine PX. Right. And then we have x prime L equals to 0. So negative PA sine PL equals to 0. Okay. So from here, you know that P cannot be 0. And since here A also cannot be 0, then we have sine PL equals to 0. Just put everything to the right hand side, and then we have sine PL equals to 0. And sine what equals to 0? Sine and pi equals to 0. Okay, remember in Fourier series, sine and pi equals to 0. And from here, you can conclude that PL equals to n pi. So P equals to n pi over L. Okay, now you have your P, you have your A, you have your B. So the solution for this x equals to A cos px. A cos px, and P is n pi x over L. Okay, clear now? Alright, clear? Why A cannot be 0? You don't know the value of A, but you know the value of P, right? P equals to lambda here less than 0. You don't know the value of A, just put everything here to the right hand side. So 0 divided by PA will give you 0. Okay. Then we can conclude that this sign PL equals to 0. Then solve for P. All right. Okay, so now you have your X. You know that this solution consists of X. So of course you have to proceed with finding T. So from second equation, T prime minus alpha squared lambda T equals to 0. Okay, right? T prime minus alpha squared lambda T equals to 0. So by characteristic equation, we have M minus alpha squared lambda. Sorry, lambda is what? Lambda is P squared. So characteristic equation will give you M plus lambda squared P squared equals to 0. So M equals to negative lambda squared P squared. Okay, will give you 1 root T equals to E exponent negative lambda squared P squared T. Okay, so this come from distinct and different roots here. Okay, this come from distinct roots because we only have one root. So you know that your P is and pi L. So T equals to XE exponent negative N squared pi squared alpha squared over L squared. Okay, up to this point. Are we good? And remember, we are always stick to the expected solution. UXT equals to X. X times T. Then the third solution give you U3. X is A cos n pi X over L times with E exponent negative n squared pi squared alpha squared over L squared T. Okay. And here consists of n, a sequence of n, a sequence of n. And this is a constant. This is a constant where now we can just simplify this U and xt equals to A times E. It's another sequence. Then we just create another constant. Okay, an cos n pi x over L exponent n pi alpha over L squared t. So this is the solution for the third case. Okay, understand or not up to this point? We have considered all cases of lambda, lambda 0, lambda greater than 0, lambda less than 0. And all of the cases will give you the solution for UXT. Okay, and the second step is to sum up all cases. your uxt equals to u1 plus u2 plus u3. Okay. Uxt equals to u1 is what? U1 is D. So D. U2 is 0. Okay. And U3 is an cos n pi x over L. So it is the summation from n equals to 1 to infinity an cos n pi x over L exponent negative n pi alpha over L squared t. So this is the solution of uxt. Okay. D plus 0 is 0. Okay, clear not? So now this is the solution. Okay, this solution comes from the expected solution of uxt here. This is our expected solution. Okay, and then by considering all cases of lambda, this expected solution fulfill the value of x and t. If one of those is 0, then we just put no interest. But if there is a value of it, then we consider all solution. So uxt equals to d. But for u2 equals to 0. Don't worry, just put 0 at the end of the process. Then we just can sum up all cases. So D from case 1, zero from case 2, and this is from case 3. And we sum up all cases. Then we have this uxt. And this uxt comes from the expected solution of uxt equals to x times t. Is that clear, guys? Up to this point, anyone has question? Are you okay, guys? Right? It is quite long, but be careful because it is doable. Okay, you do it one by one. Okay, now, of course, we're not finished yet. Not okay? For which part? Not okay? You do understand the steps, right? You do understand the steps. Can you follow the steps? Okay, so the problem here now is in terms of algebraic expression. It is quite a complicated expression, but once you understand the steps, you can try to do it again by your own and you will get better understanding. Okay? So after this, you can try to take a look again and do it again by your own so you can understand better. Okay. So now, once you conclude all solution of UXT here, remember our problem here is PDE. And we just now consider the boundary condition. But we have another condition, ux0 equals to 0. So in order to use this condition, okay, we can the rest of the constant value. As you can see, the solution still has constant. So in order to find the constant, we need to consider all conditions given, right? So of course, you have done with finding uxt, all right? But now we still have another condition and we still have another constant. So in order to solve the problems of the constant and the condition, then you just need to apply the given condition. So the given condition, another given condition is ux0 equals to x. Okay, so now you have your uxt. So we need to consider another condition, ux0 equals to x. Okay. So from here, ux0 equals to x, just consider this solution, ux0 equals to x, where t equals to 0. So now ux0 equals to d plus summation an cos n pi x over L exponent to the power of 0. When t here equals to 0, then it becomes 1, right? So you apply ux0 equals to x, then we have ux0 equals to d plus summation from n equals to 1 to infinity an cos n pi x over L times 1 equals to x. Okay, so back to the Fourier series, this can map to a Fourier series of a naught over 2 plus summation of an cos n pi x over L equals to x. So this is a Fourier cosine series. And as you can see, this is mapped to the given expression here. And if you compare these two, you know that your fx equals to x, your L equals to L, and your D equals to A naught over 2. Then you can find by solving the Fourier series here. Okay, so let's try to solve this. All right, are you following? Okay, so from here you know that fx equals to x, L equals to L, and A naught over 2 equals to D. Okay, and by Fourier cosine series, you know that A naught equals to 2 over L, integrate from 0 to L, fx dx. By Fourier series, A naught can be obtained from this formula. And L is L. Okay, L is L, fx is x. So integrating this will give you L. Okay, solving this will give you L. Just integrate. Then A naught is L. A naught over 2 is D. Right. So D equals to L over 2. Then you can have your D. Is that clear or not? Are we good? Okay. And then look at this one. AN is AN. So how can you find AN from the Fourier series? AN equals to 2 over L. L is L. Integrate from 0 to L fx cos n pi x over L. Then you can have your AN from solving this Fourier series. Then you just can substitute to this AN. Okay? So here we have 2 over L by tabular method. We are going to have L of n pi check and x over L plus L squared n squared pi squared cos n pi x over L. Integrate this by tabular method will give you 2L over n squared pi squared cos n pi is minus 1 to the power of n minus 1. So this is your AN. Now you have your D and you have your AN. Substitute to this D and AN to give you a full solution of UXT. So the final solution of UXT will give you D is L over 2, summation from n equals to 1 to infinity of AN to L over n squared pi squared minus 1 n minus 1 cos n pi x over L exponent negative square t. So this is your, okay, any question? So usually in your final, chapter 5 PDE here consists of one question of 20 marks, 15 to 20 marks. Okay. All of these steps will give you around 15 to 20 marks. Depends on the equation, depends on the cases, depends on the function. All right. But the process of finding the solution for whichever cases of zero endpoints or insulated or mixed endpoints will use the same steps. Final will have, I'm not quite sure, usually is up to six I think. I'm not quite sure. So rugi. But usually, sometimes case 1 is 0, case 2 is 0 only, and only need to find the solution of case 3. Okay. If all cases give you the answers, usually 15 and 220 is not enough. But you know, that is the process. Okay. Tomorrow, test 2, I'm not sure how many questions. But the topics are given, right? It is excluding the application of second order and also excluding convolution theorem. onwards, right? Okay, so no solving IVP, no solving BVP by using Laplace, no solving system of differential equation, only up to inverse. Okay. The question, I have to check first which, if you have okay, I have to check first. Okay. All right. Any question for this topic? I'm not going to proceed with another example. Okay. I'm just stick to one example per day. So last video, I gave you one example, right? So today, one example of insulated. So next class, we're going to proceed with the mixed endpoint example. So we have done with zero endpoints where you just apply U directly. Now, today we apply insulated endpoints where we have to differentiate U with respect to X in order to apply the condition of UX. Okay, so after this, in our next class, we're going to proceed with a mixed endpoint. And as you can see, the process of the types of boundary conditions here will use the same process. But of course, it is quite long and it is quite such an algebraic expression that you have to know how to factorize, how to integrate. The basic one is there, okay? But depends on the equation. Okay? Clear? Are we good? I'm not saying this is easy, but it is doable once you understand. Okay? So from 1 to 10, where are you for this topic? All right. Okay. 11 out of 10. Wow, good. Okay. All right. So of course, in order to understand better, of course, you have to try to do it again by your own and try with another exercise. If you have problem, you can ask me. Okay? I can review again the video after this. All right. So any more question before we stop? No more question? How about the rest of you? From 1 to 10, where are you? No more. Don't be shy. It's okay. All of you are learning, right? Section 33. Okay, so I think no more question from you. Right, so that's all for today. Okay, if you have problem, you can ask me later. All right, and then I think that's it. Let's end our class with Suratul As and Tasbih Kifara for Muslim, and don't forget to scan the attendance. Okay, guys, thank you. Assalamualaikum.